So I'm going to write a parser for the thing compiler now, and I'm going to just start by parsing out expressions like 1 plus 2 multiplied by 3. Since the parser will need to create an abstract syntax tree, I'll start with an AST package. And in an arithmetic expression, I'll just have integers and binary operations. So I'll create an int node here, and we'll just say that the value for that for now will just be int64. And then the other kind of node I want to create is a binary node. So this will have an operator, which will just be a token kind. So we can say, for example, it's token.plus. It'll have an LHS, which will be a node, and an RHS, which will just be another node. So that's the left-hand side and the right-hand side. Node for now will just be defined as any. So a parser will need to keep track of it will need the file that it's working on, because that has the slice of the tokens. We'll need a position in the token stream, so this will be an int. And we'll need the next token in the stream. The way I'm going to use the parser is just by having a main parse function that will take in the file. So this will be a token pointer file. And it's going to return some AST node. So this needs to reset the internal state. And we'll need the ability to advance through the token stream. So when we consume a token, we need to move to the next one, which means increasing the position and resetting the next token. So I'll just have another helper function here on the parser called advance. And I always expect there to be an EOF at the end of the token stream. So if next kind equals token EOF, then we'll just return and do nothing. So I could actually change this to -1 and advance. So the parse function needs to basically decide what to do next based on the next token in the stream. So we could say, for example, if p.next.kind equals token.int, then we can return an AST int where the value is some value. So in this case, the token, we could use the lexeme, so we can get the lexeme from p.file.lexeme, passing in p.next.start and p.next.end. Then we can use that lexeme to call the strconv package to parse out an integer. We'll say it's base 10, 64 bits, and then use that value in there. And because by this point we've already consumed the token, we can call advance again to make sure that the next piece of code is ready to look at what the next token is. If we didn't see an int, then we'll just return nil. And a parser is going to be a bit difficult to create automated tests for until I've got more infrastructure around things like printing. So I'm just going to test by creating a main package and printing things from the main function. So if we've got a file, token new file, I'm going to implement this as a Pratt parser, so I'll call this Pratt.fin. We'll need a scanner to scan the tokens into file. And then when we call parser.parse, this will take the file and return some AST node. So I'm just going to JSON marshal this. Just so it's a bit easier to read in the terminal. So if I try running this, we get an ast.int node with a value of 1, because the 1 is the first token in the token stream, and that gets turned into the ast node because we hit this condition. So we want to create an AST based on this entire expression. We don't want to stop on just the first token, we want to keep on going until the end of file. So there's two different ways that we could create this. We could either say that it's 1 plus 2 multiplied by 3, or we could say that it's 2 multiplied by 3, and then the plus 1 goes on the top here. So this is like a left-leaning tree, and this is over here is a right-leaning tree. And if we look at the way that we would put the parentheses into this expression, if we put the parentheses around the 1 plus 2, that matches up with this subtree down here, whereas if we put them around the 2 multiplied by 3, that matches up with this subtree down here. So we know for this expression, based on looking at it, that we would want to do the right-leaning tree because the 2 and 3 are paired up with the asterisk here. So one thing to notice about the trees, then, is that the operator that you want to do first actually comes lower down in the tree. So it gets created deeper in the tree. And the other thing to notice is that when the parentheses were on the first operator, we had the left-leaning tree here. And when the parentheses were around the second operator, we had the right-leaning tree here. So the right-leaning tree is actually allowing us to evaluate things from right to left, and the left-leaning tree is allowing us to evaluate things from left to right. So this direction of the tree comes into play when we're talking about the associativity of operators, and the depth of the tree and where the operators are in the depth comes into play when we're talking about the precedence of operators. So the first thing we'll do is just look at how we can create each of these trees. So if we create a new function here called parse-left-tree, which can return an AST node, we'll say that we'll build up a node by just creating a variable, making it equal to AST node, returning the node at the end, and we will just start out with this code that we've got to parse the integer. So we're just immediately setting node equal to the int and then just returning it. So if we have a look at the expression 1 plus 2 multiplied by 3, if we want to parse this as a left-leaning tree, what we can do is say that we know that we're in the parsing arithmetic expressions right now. We don't support unary operators, only binary ones. So when we first call the function, we'll just assume that there's an integer there. So by the time we've advanced here to reset the internal state, p.next is pointing at the 1 here. So we can basically use the p.next to create the integer, and then we advance again, so p.next is now looking at the plus token. So at this point we can basically decide what to do. We can either say that if it's a binary operator, we'll start building a binary node to create the tree. And if by the time we reach the end it's EOF, we'll just return from the function and return the tree that we've built. So because we want to consume all of the tokens, we'll just loop until we reach EOF. And each time we consume an integer, we'll just see if the next thing is a binary operator or not. So far we've got an integer. So we've got 1. Then p.next is looking at the plus, and we know that that's a binary operator. So we can start building the tree. And so we know that the thing that we've parsed so far is on the left-hand side. So when we start building the binary node, the one that we've built so far should go in the LHS. The plus here is like token.plus, so that will be the op. And then we need to decide what to put on the RHS. And what we can say is that, well, if we're on a binary operator, it doesn't make sense for anything other than an integer to come on the right-hand side. So we'll just parse another integer and put it on the right-hand side. So we'll get the 2. After we've got the 2 and we've created the tree with the binary node, the p.next will now be on the asterisk here. And we can basically do the same check. We can just say, are we on a binary operator or are we on EOF? Because we're on a binary operator, we'll basically start building another binary node. We can see that everything that we've parsed so far is on the left-hand side, so the binary node should be created with the stuff that we've got so far on the left-hand side, just like we did when we had the 1. And then again, it's a binary operator, so we'll just assume there's an int on the right-hand side here. So we'll parse out the int. We'll set that as the right-hand side. We'll look at the p.next. This is EOF. Because it's EOF, there's nothing left to do, so we just return the tree that we've built. So for the whole time that we're not on EOF, we basically just want to loop over all of the tokens. So we'll say that for p.next.kind is not equal to token.eof. We're basically going to check if the next operator is a binary operator or not, or the next token is a binary operator or not. So we can switch on p.next.kind and see if it's one of token.plus, token.minus, token.asterisk, or token.slash. And if it is, we want to start building a binary node. So we know that the binary node is going to be, it's going to use the LHS will be the node that we've built up so far. So we'll say node equals ast.binary, the op is going to be something, the LHS is the node we've built up so far, and the RHS is also going to be something. So to get the op, we know that that's going to be whatever the binary operator's kind is, so we can save that out here as p.next.kind. And then we've consumed this token and we want to move on to the next integer to make sure that we're ready to parse another integer. So we'll say p.advance here. Then we know that we want to always just assume there's another integer on the right-hand side of a binary node. So we'll just parse out another int here, but instead of replacing node, we'll save it off into another variable. So we can use RHS as the value down here, and we can use op as the value out here. And so now if I run this, we get a tree where the LHS is growing because it's expanding the left-hand side by constantly putting the thing that we've got as the left-hand side of the new tree. So we're sort of building a left-leaning tree by going up in an iterative loop. So now we'll just have a quick look at how we can build a right-leaning tree. So if we parse right tree, and we'll just call the parse right tree function up here. So if we have another look at the expression again, so we've got 1 plus 2 multiplied by 3. So we know that p.next is on 1 as we come into the function. We're going to do the same thing, we're just going to assume that there's an integer. So we'll say this is 1. The next thing we need to do is, again, we want to consume all the tokens until the end, so we'll just keep on going until we see an EOF. So this code for the integer and this code for the loop is still fine. We know we want to check if next is on a binary operator or not, so this code is still the same as well. And we can start building the tree. We know that the stuff that we've built up so far is definitely on the left-hand side, so we can just, set the node that we've built up so far as the LHS. And now we need to decide what to do about the right-hand side. And to build a right-leaning tree, we basically just want to fill up the right-hand side with trees until we reach EOF. So because we're trying to build up trees, and this function already knows how to build trees because it's got the function, it's got the binary AST node in here, we can just call the function again recursively. So if here, instead of assuming that there's just an integer, we'll basically call ourselves at this point. So we'll create another call stack, or we'll create another stack frame here when we make the function call. We come into the function call, we assume that there's an integer on p.next, which it will be by this point. This will be 2. So we get the 2 out, we advance, we've got an asterisk, we know that's a binary operator and not EOF, so we start building a tree again. The 2 goes on the left-hand side because the 2 is on the left-hand side. Then to get the right-hand side, we create another stack frame by calling the function again. This one, again, assumes that p.next is on an integer. So we get 3. We've advanced now to the EOF by this point. So this loop condition comes back as false. It immediately returns the node, so it's going to return 3 at this point. So this 3 here returns from the function call and becomes the RHS. This then loops back up to do the EOF check. This evaluates as false, so we drop through and we return the node so far, which is now this tree. So this entire tree returns up the call stack to become the right-hand side for this top-level tree here, and that's how we can build a right-leaning tree. So all we're doing is we're getting rid of this assumption that there's just going to be an integer, and we're going to parse trees all the way down the right-hand side. So if I run this now, we can see that the RHS is expanding because it's growing, because we're building a right-leaning tree by expanding it down with more trees on the RHS. So if we go back up and look at this left tree one though, we can notice that basically this code here to get the integer and this code here to get the integer are exactly the same. And when we create this binary node, if we just call ourselves here, the first thing that will happen is that we'll create an integer anyway. So we could remove this code. We could call ourselves with a Boolean value to tell the function whether we want to just return the integer or not. And if it's true, we could just return the integer here at this point and never go into the loop. And that would achieve the exact same effect as parsing the integer at this point here. So we can actually define parse left tree with a stop parameter. We know that we've got an integer at the very beginning, and if stop is true, we'll just return the integer that we've parsed, which means that we can get rid of this code and replace it with a recursive call to parse left tree with the Boolean value true. So this has the exact same effect as the previous version of parse left tree, but we've defined it in terms of some kind of recursion. So we've recursively called left tree, we've passed in a Boolean to say that just give us the integer back and don't recurse any further. So if I call parse left tree now, we'll see that, oh, I need to pass in a variable here. So the first time that we call this function, we don't want it to stop immediately, because if we pass true into here, it's going to parse a single int, stop immediately, and that will be the end. but we want it to loop until it gets to the EOF, so we have to pass false in here as the first argument, and then we pass true in the loop down here to make sure that it stays in that loop and builds up a left leaning tree. So now LHS is expanding again because we're building a left leaning tree, but what this means is that if we pass in false, it will always fall through here, which means that it will always hit the recursion, and it will build a right-leaning tree instead. So RHS is expanding out in this run. So what that means is that we don't actually need this parse right tree function, and we can rename this one to just parse tree. So now we have the ability to choose which way we're going to build the tree. If we pass true into this loop, sort of the function call in the loop, passing true means that it will return immediately and make a left-leaning tree, and passing false will make it recurse and create a right-leaning tree. So if we have a look at a few expressions here, we've got 1 plus 2 plus 3. Let's say 1 multiplied by 2 plus 3. And 1 plus 2 multiplied by 3. So if we look at where we would put the parentheses in these expressions, we can tell visually just that the two additions have the same precedence, so we would do it left to right. We want to do the multiplication first, so in this one we do the first operator, and in this one we do the second operator. And because we saw that the parentheses match up with the subtrees, we know that this one is a right-leaning tree, and we know that these two are left-leaning trees. So we know that in the main file we've written this expression, so we could just hard code it to create a right-leaning tree for us, and that would create the correct AST structure. But then it would be incorrect for these two here. So we need a way to dynamically choose which direction we're going to build the tree in based on the powers of the operators. And that's basically what a Pratt Parser is doing. So if we have a look at the operators here, and we say that in relation to some operand, the operator on the left-hand side is called the previous operator, and the one on the right-hand side is called the next operator. And if we look down this line here, we can see that basically the parentheses are deciding which operator it should bind to. So in this case, the 2 is binding tightly to the previous operator. Same in this one. And in this case, the 2 is binding tightly to the next operator. So if we call this one the previous operator, and this one the next operator, for each of these, we can notice some pattern, which is basically that when the powers equal each other, so when the previous power equals the next power, we want a left-leaning tree. When the previous power is greater than the next power, we want a left-leaning tree. And when the previous power is less than the next power, we want a right-leaning tree. So this one creates a right-leaning tree. And then if we combine these two, we can say that if P is greater than or equal to N, then we want a left-leaning tree. So now we can see that we have this Boolean condition down here about whether we should be creating a left-leaning tree or not. And the Boolean, the condition that tells us whether we want a left-leaning tree is this one, which would evaluate to a Boolean. So we should be able to plug this into here and say that if P is greater than or equal to N, that is when it should stop. So we just need to figure out where to get this P and N. Where do we get the previous power and where do we get the next power? And if we look at the naming of things here, this p.next being assigned to an operator is a pretty strong clue that p.next is going to be the next operator. So let's imagine that we've just called this function and we are assuming that we are on an integer. So we get, for example, the 1 here, and then we advance so that p.next is on the plus. Well, by the time we've advanced at this point, p.next is on the plus, so that's where this is coming from. And in relation to the 1 here, the p.next is the next operator. So then where do we get the previous operator or the previous power from? Well, when we call this function recursively, we're going to find another integer, which in this case might be, for example, 2. And the previous operator to 2 was the next operator in the previous call. So what we can do here is that we could save some value n, which would equal the power of the next operator. And then when we call this recursively, we just want to pass n in to become the previous power. So up here we would have p. So now we know where p and n can come from, we can compare these things in the function. So let's say, for example, that we want to know whether we should create a left-leaning tree, so that's the condition we need to evaluate here. So this will be previous power is greater than or equal to the next power. And we can look up the next power based on the operator. We know what kind the operator is, so we can just create a table of powers to look up into. So let's say next power is equal to powers where we look it up by the p.next.kind. And we'll create the table of powers up here. So we'll say powers equals some fixed array of integers, where we'll say that token plus is the power 1, token minus is the power 1 because they're the same, and then asterisk and slash, they will need to be higher powers because they should have precedence over addition and subtraction, but they should also be the same because they're the same power as each other. So that gives us the next power down here that we've said that we can then pass into the next call to become the previous power for this next call. So this will be previous power up here. Okay, so the next thing to notice about this though is that if we are evaluating this condition here, this will evaluate to true or false, which will be immediately assigned to this stop, which is then immediately just used here anyway without any change. And we already have the previous power and the next power variables, so we could just remove it from the call, get rid of the stop, and replace the stop here with the conditional with the comparison directly. After we have parsed out an integer, we've already advanced to the next token, which will be an operator. So we can move this assignment for next power earlier so that we can use it in the condition here. So now we have next power and previous power, which we can easily use to tell whether we're supposed to be creating a left-leaning tree or not. Now, since this is dynamic and the next power can change, let's say that we're creating a left-leaning tree, which means that we're going to be using this loop. So if we remember, the left-leaning tree is created primarily through just looping over and over again here, whereas the right-leaning tree is created by recursively calling over and over again. So in the case of recursion, we don't need to worry about reassigning anything. We're just passing in the next power, and that's what keeps the previous power up to date. And then we just keep on looking up the next power as soon as we get in there. But in the case of the left leaning tree, we need to make sure that we update next power again. When we first come in here, we parse an integer, and then we assume that we're on an operator, so we look up the power of the next operator. Then when we come into here, we parse another integer through this recursive call, assuming that we actually stop and we bring back the integer. Now next is on a different operator, so we need to make sure that we update the next power. Then we only want to continue. We only want to continue doing this loop where we keep on building up the tree if we are building up a right-leaning tree. So we also need to keep a condition in here as well, because if we have fallen into the loop to build up a left-leaning tree, what would normally happen is that we would immediately check the next operand and see if we're supposed to return or not. But if we're looping around and we've updated the next power here, we need to check if we need to return or not again. And returning is basically the same as skipping this loop and then allowing it to return down here. So we need to update the next power so that it matches up with the next operator. And then we need to check to see if we should still be looping or if we should be immediately returning or not to match the functionality of this initial check here. And if we're doing that, then that means that this initial check would be the same as keeping a check in the loop condition for the opposite. So basically what we want to do here is take this condition, use it as the condition of the loop, but we only want to loop. So in other words, we only want to enter this loop if we are not creating a left-leaning tree, which means that we need to flip the comparison to say less than. If we are creating a right-leaning tree, then we want to do the loop so that we can recursively go down. If we're creating a left-leaning tree, we want to skip the loop so that we immediately return our integer. So we create our integer. If we're creating a left-leaning tree, we skip the loop and return the integer. If we're creating a right-leaning tree, we go into the loop and we try the recursion. So now in the initial call to parse tree, we're still passing false because we don't want it to immediately stop. We want it to have the chance to try and recurse or try and decide what to do based on the powers. So we need to make sure that this condition is triggered so that it gets the chance to try and do the recursion, because we don't want it to just immediately return the integer on the first call. So we need to make sure that this condition evaluates to true on the first call. Since our lowest power is 1, the way to make sure that this would evaluate to true would be to make sure that the previous power that we pass in is lower than any other power, so we can pass in 0 here. 0 will be lower than any other power, so that would mean it goes into this loop, tries to see whether we're on an EOF or a binary operator, and then it would do the recursion to see whether it should, again, return the integer straight away, or whether it should try and do some recursion to build up more of a right-leaning tree. So let's see if I've missed anything. Okay, so we get 2 multiplied by 3 plus the 1, which is correct for this expression here. Now if we switch these operators around and try it again, we get a 1 multiplied by 2 plus the 3, which is correct for this. And finally, if we make them the same power, the left-hand side expands out because it's left associative. They're both the same power, so we want to do the left side first and then the right side. We're going left to right, so it's 1 plus 2 plus 3. And that's basically how Pratt parsing works. There's a little bit more that we can do though. So for example, we can start refactoring this to shrink this function down. We'll, instead of calling this parse tree, we'll call this parseExpression. And instead of calling this node, I'm just going to call this expert as well. And then we can basically move the node creation out into helpers. So we could say that expert equals p.makeInt. So we'll create a make ints down here, where we just return the AST int. And then here we can do a make binary. Oh, and actually, I said that we should keep the next power up to date, and then I forgot to do that. So we need to say that next power equals powers p.next.kind. And we want this to happen on every iteration of the loop, so I'll move it outside of the switch. But within the switch here, we're creating a binary node, so I'll just replace this with expert equals p.makeBinary. And we'll need to use the thing that we've built up so far as the left-hand side, so we'll pass expert in. So we will return expert. And instead of using expert here, we'll use LHS. Then we need to look up the power within this function, make binary. So we're going to look up the next power by querying the powers table with p.next. Well, this will we'll just use op here because that's already p.next.kind. So if we run this, we get the same result, and I'll just put a asterisk here to make sure that we're building out the right-leaning tree correctly, which we are. So the next sort of refactor might make more sense if we expand the capability of this a bit. So if we go back here, instead of just trying to parse out ints, if we also try to parse out identifiers and I run this, we'll see that we get a value of 0, and that's because we're always trying to parse an int. We've got an identifier. We're always trying to make an int which is erroring on the parse int call down here, so value is 0 and we return an int. Instead, what we want to do is decide based on the next kind. So we'll want to say, for example, in the case that the next token is actually an int, then we want to make an int. Otherwise, if it's an identifier, then we'll make an identifier. So to do that, we can just copy this make int down here. Change it to make ident. We don't need to parse an actual integer anymore. And we'll create a new AST node, which we'll call ident. So over in AST, we'll just create a new one. Ident name is a string. And we're just assigning lexeme to be the name here. So now if I rerun this, we've got LHS is name ABC, which is correct. But you'll notice that basically we're using this kind to decide which function to call. So we could move this into a table where we look up the function pointer by the next token's kind and then just call it. So we'll create a table in the parser because we're calling functions with p dot something. We need to create the table in the parser so that we can keep it using the correct functions and keep the parser's state around. So we'll create, I'm going to use the term prefixes for these functions. So these are prefixes because they are the functions that you call at the beginning of an expression. So these functions create the start of an expression or the prefix of an expression. So prefixes is some table which we'll say is token kind count elements long. So we'll go to the token package and add a new value to the end of the enum, and we'll use that as the constant size for the function table. Then what we need to do is when we create the parser, we need to just create the table as well. So we'll create this table, and we'll say that if we see an int that maps to p.makeInt, and if we see an ident that maps to p.makeIdent, and then we'll return p. So now down here, instead of using this switch, we can basically just set expression equal to p.prefixes, look up the function by the next kind, and we'll just assume it exists and call it. So that still works fine. We're doing the same thing here with this kind. We're looking up a function to call. And to make this one a bit more obvious, I'm going to add a bang character, so the exclamation mark. And we'll say that when we do a bang character, we're going to do factorial. So this will be a postfix. A postfix node, because there's no right-hand side, there's only a left-hand side. So for example, we'll want to basically say ABC plus 2 factorial multiplied by 3. So we need to add to the scanner, we'll need to add a new token. So we'll add a test. This will be line 8 now, column 3, and this will be line 9. We'll add it to the punctuation table. Let's run the test. Okay, yes, parser has no postfix, so I'll just comment this out for now. Okay, so the test seems fine. So in the case where we see a bang token, we want to call this postfix one, which we don't have yet, so we'll just create it. So the difference between make binary and make postfix is that if we look at the 2 factorial back here, the factorial operator only has a left-hand side. It's going to bind tightly to this 2. So we basically want to have make postfix, where we take a left-hand side, that will be the 2. We don't need the next power, because we're not going to try and parse an expression for the right-hand side. We just need to assign the LHS and return a postfix node. We'll call this unary postfix. And we'll call this make unary postfix. So in AST we can copy this binary node, we'll call it unary postfix, and we'll get rid of the RHS. Make binary, let's see. Oh, I think that is because, let's see, 47. Yeah, so basically, because it's an operator, I need to associate it with a power as well. So if we've parsed the number 2 here, then p.next is going to be pointing at the bang token, and we have to be able to look up a power for it, which doesn't exist right now, so I'll add 1 into the table here. And we're going to set this as 3 because we want it to tightly bind to the 2. I'll show you what happens when we put an incorrect power here as well. So if we run this, we've got the factorial of 2 being multiplied with 3, and then that's being added to ABC here. And if we just make these the same operator, so plus and plus, we have the factorial of 2 being added to ABC being added to 3. So this is working correctly. So let's just put it back to the multiply, where we get the factorial of 2 being on the left hand side of the multiplication. If I change this to some lower power, it's going to bind the factorial operator to more of the expression that comes before it. So if we run this now, the factorial is basically bound to the entire addition of ABC and 2. So it's as if we parenthesized it like this. But we want to parenthesize it like this. Or like this. So in order to do that, we want it to bind tighter to its operator, so we're going to give it a higher power. And that works correctly. So basically we've got the same situation here. We're just looking up a function to call based on the next kind. If it's one of these, we'll call make binary. If it's the other one, we'll call make unary postfix. So we can do the same thing, and we're going to call these functions infixes because they come after the beginning of an expression and they accept something on the left-hand side. And they may be unary, they may be binary, we may be using them to do things like parsing out a ternary expression or something like that. So we'll call them infixes because they're operators that go somewhere in between operators. And they always accept an LHS, which is why we always have to pass in the expression so far. So we'll call this infixes. These are functions that accept a node and return a node, and we'll do the same thing where we'll just build up a table. So we'll say in the case of plus, we'll make a binary node. This will be the same for minus, asterisk, and slash. And then in the case where we see a bang token, we want to make a unary postfix. So now we can get rid of this switch, and we can just say that expression equals the p.infixes, look up the function pointer by the kind, call it immediately, passing in the expression, and then update the next power. Oh, I think I need to change this to accept a node. Okay, and that works correctly still. So we could move the powers up to the top and leave it like this, but I want to do a bit more refactoring. So we'll create some constants. We'll say power none is iota, power term, power factor, and power unary. And we'll replace these numbers here. So these two are power term, these two here are power factor, and this one down here is power unary. And when we first call the function, we'll pass in power none. Okay. The next thing I'd like to do is basically group all these things up, because you can see they're basically related. These powers always match up, so we've got kinds here, and these kinds always match up with the kinds that are here. So an infix always has to be associated with a power, so they may as well be in the same table. So we'll create a new type here called rule. This will basically take a prefix, which will be the function that returns the AST node. We can take an infix, which is a function that accepts an AST node and returns an AST node, and we'll have a power. So now, instead of creating a table, a separate table for each function kind, we'll basically just have a table of rules. We'll move all of these ones up into here, get rid of this one. Instead of prefixes, we'll have rules. So we'll change this one to rules, and this will be a table of rule structs. Then we just need to change this so we've got a prefix for the first two, and then these ones are all infixes, and these ones each have a power that matches up with the powers I've put in the table up here. So we'll just take these powers and put them in here. And then we can get rid of the powers table as well. So anywhere that we're using powers or anything in any of these tables, we now need to look up based on a rule. So the first thing we're going to do is look for a rule in the rules table based on the kind. And then we're just going to use the rule. So we'll just say rule.prefix, we'll call that. The next power is basically just going to be rule.power now. But here we're updating the next power, which means we actually need to update the rule at this point. So we'll just have the code to update the rule, because we can't update a next power directly anymore. And we're updating the next power down here, so we need to update the rule again. We're also using the powers table down here, so we can just look up a rule based on p.rules, p.next.kind. And instead of next power, we'll just call rule.power. Let's just try and run it and see if I've missed anything. Infix is undefined. Yes, I'm still using infixes here. So if we look at this condition here, we only want to call an infix function if it actually exists. If it doesn't exist, we're going to crash. So we could just replace this EOF check with a check to see if infix is not nil. And then we can just use p.infix here. Or rule.infix, I mean. And now we get exactly the same result, but we've moved everything into a rules table instead. So the other thing that this rules table structure highlights is the fact that a token can be associated with both a prefix and an infix at the same time. So I said earlier that we didn't support unary operators like a unary minus, so we can't do things like -1. If I come back to here and we change this expression a little bit, let's just say we've got negative ABC plus 2 factorial plus 3. If I try and run this, we get a nil pointer dereference, and that's because the minus is now in the prefix position. It's in a position that's trying to start an expression, which means that as soon as we come into parseExpression, we try to look up a rule based on the minus token, then we try to call a prefix function, which doesn't exist, it's nil. So in the minus table here, we could just add some behavior for it in the prefix position. So we could say p.make unary prefix instead. So if we go to the AST, we've already got unary postfix, we'll just create unary prefix. And a unary prefix has a right-hand side, so the negative minus has a right-hand side operand, but it doesn't have a left-hand side. So we'll change this to RHS. We've got make unary prefix, so we'll basically just copy unary postfix, and the difference here is that we don't have a left-hand side, so we don't need to take this LHS in, because it's in the prefix position. We're going to call the prefix function, which doesn't take an AST node as an argument. We'll change this to prefix, and then all we need to do is that instead of LHS, we need RHS, and we're not being parsed an LHS anymore. Instead, we want to parse the next part of the expression, so we need to call parseExpression. And we need to decide what power to pass in here. So I'll just show you what happens when we pass in a couple of different powers. Let's pass in power unary first. This will be the obvious one, because if we're making a unary prefix, we want the unary operator to bind tightly to its operand. So we'll pass in power unary, because that power is higher than any other operator's power at the moment. So let's just see if I've missed anything. RHS in postfix. Okay, I need to change this to prefix. So we'll try running again. So now we see that we've got the addition of minus ABC and 2 factorial, which is what we expect. So the unary minus is being applied to only ABC. If we change this to be something like power none, this means that the unary operator is going to be bound to the entire expression after it. So now if we rerun it, we can see that the unary minus is actually at the top, and the RHS for the unary minus is actually the entire expression. So now it's behaving as if we've parenthesized this expression and we're negating the entire thing. We want it to be parenthesized like this, so we're going to leave this as power unary. And we get the correct result. So there's one more thing that a Pratt Parser can do. Oh, and I should mention that. So basically, we can associate a token kind with both a prefix and an infix function, which means that when we see the token in a prefix position, so that is when we see it starting an expression, we can give it one behavior. And when we see it in the infix expression, which is after the prefix, so it has a left-hand side, we can give it another behavior. So other examples of this might be, you could do a unary prefix for the plus for positive. You could do a unary prefix for the asterisk, which would be like the pointer dereference syntax in C or Go or something. And we can see that the unary postfix takes in a left-hand side, so that's why it's an infix for the factorial bang down here. So the other thing that we could do as well, or the other thing that Pratt parsers can do, is a right-associativity. So if we have a look at the expression, for example, we've got, let's say we've got A plus B plus C. In this case, we're parsing left to right. Because they're the same power, we want left associative, so we parse left to right. And that's where the whole thing of if these two operators have greater than or equal power, we do the left, because if they're equal, we want to go left to right. And this works for our case, that's basically what we want. But there is another case where, for example, if you had assignment as an expression, in this case, left associativity doesn't make sense. We can't assign C to the result of the assignment of A and B. In this case, we actually want right associativity. So in this case, when the two operator powers are equal to each other, we want right associativity instead. So this right associativeness, if we do A equals B equals C, we want to say that if these are equal, then we want to build a right-leaning tree instead. And right now, because these are equal, this condition evaluates to false, so it skips it, which means it's going to build a left-leaning tree. So to make this true, we could change this to less than or equal to. So this equal to is the thing that decides the associativity. And if it's equal in this case, we're going to build a right-leaning tree because of the recursiveness. But then this means that our normal case of, for example, addition or subtraction would also become right associative, which we don't want. So the other way to do this is that it only matters in things like binary nodes. These are two nodes that go together as a binary node on the assignment. So what we can do here is we can check to see if the operator in the rule should be considered to be right associative. If it is, then we can just minus 1, we can just decrement the power by 1, so we could say power minus 1. Then that way, when this power gets passed in to the parse expression, it's 1 less than it would be, and this will now be true, and it will be allowed to recurse down to the right. So let's say, for example, that these two have powers of 1. We come in, we come into the parse expression. First thing we do is we get an A in the prefix position. Then we go down to the infix position, which is this assignment. So this one is going to call make binary. We then get the rule. We say that, oh, well, this is supposed to be right associative. So we'll save the power here. we'll then say, if it's right associative, we'll do -1. We pass the power in here. So now we're considering previous power here to be 0. Because at this point it was basically 1 minus 1. So when we pass it in, it's now 0 is the previous power. And because of that, this previous power less than rule power, where rule power is the next one, so that's this 1 here, this one has become 0. So now the condition for less than is true, which means it's going to recurse down to the right and create a right-leaning tree, making it right-associative. So we can build that in quite easily to the rules table here. We can say is right-assoc can be a bool. And then if we wanted to make something right-associative, we could basically put that into the table here as true. Then we can store the power, so we could say that power equals rule.power, and then say if rule.is right-assoc, power decrement by 1, and then we'll pass in the power. So if we go back and parse a simpler expression, so we'll say 1 plus 2 plus 3 plus 4. So these are all the same power as each other, so they should go left associative, so they should go left to right, which is why the left hand side is expanding out, because we're doing 1 plus 2, then plus 3, then plus 4. But if we go back up to the token kind for plus, and in the rules table we now say is right-assoc is true, and we rerun this, now the right-hand side is expanding out because it's being allowed to recurse down the right-hand side, and so it's becoming right-associative instead. So I'll just remove that from the plus. And so that's a Pratt Parser. We aren't doing any error handling here. What we should be doing really is checking to see if the rule exists, and if it doesn't, we'll generate an error and all that kind of stuff. But I'll leave that for another time. So we've got a fully working Pratt Parser. We can associate token kinds with both prefix and infix functions with different powers. And we have the ability to, if we want to, decide if a particular operator should be right associative or not.